Hi, my name is Kevin, and I will be presenting on some recent work done in collaboration with Yair, Carmon, Yujia, and Aaron Sidford, titled Coordinate Methods for Matrix Games. This talk will be given in 4 parts, 2 of which will be by me, and 2 of which will be by Yujia. We study a problem family known as bilinear saddle point problems, or SPPs. These are minimax optimization problems between a min player living in X set and a max player living in Y set. The objective function is linear in both variables, and throughout this talk, we will call the interaction matrix between the players A, which will be m by n. This basic family captures many fundamental problems of interest in optimization, learning, and economics. By fixing domain geometries of both players to be probability simplices, the problem becomes a zero-sum game, which also captures linear programming. We call this an L1-L1 setup. An L2-L1 setup, where the X player lives in a Euclidean ball, encapsulates linear classification. And an L2-L2 setup is the primal dual form of linear regression. More generally, efficient large-scale minimax optimization has received significant interest due to its role in capturing an adversary in various problems in modern machine learning. The main question our work addresses is that of efficient algorithm design for approximately solving this family of problems. The notion of approximation we will consider throughout the talk will be duality gap, or the change in objective value when players shift to best responses. We'll start by giving some context, focusing on the L1-L1 setup, matrix games. The existing literature offers methods supporting a range of trade-offs to solve these types of problems. One end of the spectrum is interior point methods. These algorithms solve the problem in a number of iterations, depending only polylogarithmically on the desired accuracy, at the cost of expensive iterations due to solving linear systems. This makes IPMs suited for applications where the dimension is not too large, but highly accurate solutions are needed. For the rest of the talk, we focus on the large-scale regime, where we are willing to tolerate an iteration complexity polynomial in the inverse accuracy to save on the cost of each iteration. The first type of method offering this trade-off is known as exact gradient methods. These are first order based on querying gradient information, which amounts to a matrix vector multiplication. This costs n and z per iteration, the number of non-zeros of the interaction matrix. The number of iterations is linear in L over epsilon, where L is a Lipschitz constant of the problem. On the other hand, stochastic gradient methods based on row column sampling push this trade-off further, opting for cheaper iterations at the cost of a quadratic dependence on L over epsilon. The updates are based on sampling rows or columns, so they typically can be conducted in m plus n time, where m and n are dimensions in the matrix. In certain cases, we can gain further wins for matrices with sparse rows or columns. We use RCS to denote an upper bound on the maximum row or column sparsity. A recent approach pioneered by Bilinear and Bach and the authors of this paper uses ideas from the variance reduction literature in convex optimization to give an intermediate trade-off. These yield runtime improvements in many cases, based on occasionally recomputing a full gradient to design better estimators. In this paper, we push stochastic methods to their limit by designing methods updating single coordinates at a time. This is the first work in the literature for these setups that achieves near constant per iteration complexity. We show that this design strategy also gives overall runtime wins by up to polydimension factors for various types of structured matrices. One reason to opt for methods on the spectrum with cheaper per iteration costs is that typically iteration cost better captures observed performance. Moreover, this separation makes the algorithm more modular, and engineering optimizations can be made to improve implementation of each iteration. On the other hand, bounds on the number of iterations tend to be pessimistic, where structured instances seen in practice often yield improved performance. So, if we have 2 methods with similar theoretical runtime bounds, we may expect the one with cheaper iterations to perform better on real data. To capture the second idea more formally, a second motivation for our work is a notion called the numerical sparsity of the matrix, inspired by a recent work of Gupta and Sidford. In many instances arising in practice, the interaction matrix at hand is not sparse, but has many small entries. This includes physical interaction models which decay at a distance, and matrices encoding spiky probability distributions, such as neural network activations. Since sparsity notions like n and z and RCS are not continuous in the elements of the matrix, the resulting runtimes are sensitive to small perturbations. Coordinate methods bridge this gap. The intuition is straightforward. We can avoid effects of many small coordinates by sampling them less frequently. The key technical challenges which arise are twofold. First, to reflect the numerical sparsity gains of coordinate methods, we need to tailor analysis of stochastic methods to capture local notions of variance, and carefully design sampling distributions to match them. Second, We need to develop ways to implicitly maintain and query iterates in near constant time. This is challenging, especially in the case of variance reduction, where updates may be fully dense, and all m plus n coordinates may change every iteration. We will discuss these in detail in the rest of the talk. The classical sublinear runtimes of row sampling methods have an iteration complexity LRC over epsilon squared, and the cost per iteration is m plus n. Here, LRC is a Lipschitz constant of the problem associated with row column sampling, defined in the table below. The corresponding variance reduced runtimes methods have runtimes which are the geometric mean of the sublinear runtime in n and z. As a brief aside, all sublinear runtimes also assume certain types of sampling or query axis, implementable in one pass over the matrix. Our coordinate methods have runtimes scaling more favorably in terms of problem dimensions, because they attain near constant per iteration complexity. This is at the cost of dependencies on different Lipschitz constants, which we call LCO and list here. We further show that for L1 and L2, L2 setups, our constants are optimal in a restricted sense. Using the data structures we develop, we also improve row column sampling methods to have iteration costs depending on the sparsity bound, RCS. This was previously not known for variance reduced algorithms. Since LCO is always bounded by square root RCS times LRC, our coordinate methods are never worse than sparsity-based implementations of row column sampling methods. As an example, we show our runtimes for matrix games, where the maximum L2 and L infinity norms of rows and columns are comparable. Our coordinate methods improve upon row column sampling by factors up to linear in RCS for fully stochastic methods, and square root of RCS for variance reduced methods. We also use our coordinate methods as subroutines in several applications, such as computational geometry and linear regression. We obtain wins when the interaction matrix is sparse, and further wins when it's numerically sparse. These improvements will be elaborated on later in this talk. I'll now turn it over to Yujia to explain our algorithm design.
To begin with, we introduce a few problem setups and notations used hereinafter in this talk. We consider the minimax problem in form minimum over x, maximum over y, y transpose ax, where no linear terms are considered for simplicity. The iterates and gradient operators of our primal dual algorithm will have two blocks corresponding to the two players. To drive our methods, we use measurements in a primal dual Bregman divergence, which sums divergences on each component. The Bregman divergence is a notion of distance adapted to a regularizer, and is useful for mirror descent algorithm design. In our following discussion of our algorithm, we will focus on our variance-reduced method in the L1-L1 setup, since it captures most of the technical ideas. In this setup, the relevant divergence is the KL divergence. Our method follows the conceptual mirror prox framework of Nemirovsky. To solve the original minimax problem, this framework takes alpha over epsilon steps, where each step is composed of one approximate solve of an alpha regularized subproblem and an extra gradient step. Note that a larger value of alpha means more steps in the outer loop, but leads to simpler to solve inner loop subproblems, yielding a range of runtime trade-offs. What we propose in our algorithm is to solve the inner problem with variance-reduced stochastic mirror descent using coordinate-sparse gradient estimators. We choose a value of alpha which optimizes the cost of the whole algorithm composed of an inner loop and outer loop. The same general recipe was used by the authors of this paper in our earlier work on designing variance-reduced algorithms for bilinear SPPs using stochastic row column estimators. For the remainder of this part, we'll focus on the cost of each inner loop. Our inner loop uses a stochastic method to solve the alpha regularized subproblem via coordinate gradient estimators. The key property for its analysis we show is that when the gradient estimator satisfies a certain bounded variance property for an appropriate step size, L squared over alpha squared iterations of the inner loop suffice. The key requirement of this convergence guarantee is the bounded variance property. We know that it requires the square difference between the estimator and the gradient at the anchor point W0 is proportional to the square distance in an appropriate norm. One important note is that we show for L1 domains, it suffices to measure the variance under the so-called local norm, a weighted L2 norm where the weight is some arbitrary simplex variable which arises in the analysis. This is also shown as the local norm argument for simplex variables in the optimization literature. Such a variance measurement generically leads to smaller bounds compared with the standard dual L infinity norm. This is necessary for us to give our tightest bounds in terms of the Lipschitz constant L. We will refer to the second moment measured under local norms as the local variance. By balancing the cost of each variance-reduced inner loop, assuming we can achieve a desired local variance bound, with the number of loops required by the overall conceptual mirror-prox method, we achieve our claimed runtime by choosing the optimal value of alpha. To fully build this algorithmic framework, there are two questions remaining. First, how do we design stochastic gradient estimators with low local variance? Second, how do we implement each inner loop iteration in near constant time? It turns out that by using coordinate methods, we can find some nice answers to both questions. Given the bilinear structure of the problem, our gradient estimator is the sum of two vectors. The first is a fixed dense part computed once at the start of the inner loop, which is the gradient at the anchor point. The second is a stochastic estimator of the difference between GZ and GZ prime, which we write out explicitly here. For the difference estimate, we consider an unbiased O1 sparse coordinate estimator. It has the form listed here and depends on the sampling distribution of P and Q which we choose. This is different than previous work, which we weighted an entire sampled row or column. To answer the first question, the main challenge boils down to how to choose P and Q optimally for all three domain setups, so that we obtain an L bound as small as possible. This will lead to fewer steps for solving each subproblem, following our inner loop guarantees. For the second question, we build appropriate data structures for efficient updates and show an amortized, nearly constant cost per iteration implementation. This is not an easy task for two reasons. First, our stochastic gradient is not truly sparse because of the dense component, which means all coordinates may be updated every iteration. Second, for L1 domains, the mirror descent step performs nonlinear operations such as exponentiation, which adds on to the difficulty. We first talk about our near-optimal design of the stochastic gradient estimator. The goal is to choose good distributions PQ to sample entries so that the local variance bound holds for some L as small as possible. Recall that for L1 setups, we use a notion of local norm here, which is a weighted L2 norm induced by some arbitrary fixed simplex variables, called U and V here. By direct computation, the optimal choice of Pij is proportional to square root Uj times absolute value of Aij and y minus y prime, and a similar choice is the best Q. The resulting constant L is the maximum L2 norm of any row and column. However, this distribution choice is not implementable for several reasons. First, it depends on simplex variables U and V, which only come up in the analysis and may not be known by the algorithm. Second, it depends on differences between iterates, and we don't know how to efficiently modify our sampler to update differences after exponentiation. So instead, what we choose is a distribution in the following form. Pij is proportional to Aij squared times yi plus 2yi prime, and similarly for the Q side. The nice thing about this distribution is that it gives the L that matches exactly the optimal one up to constant. Favorably, such a distribution is also easier to sample from, not only because it no longer depends on UV, but also it changes the entry difference to a sum. The downside about this choice is that it gives a weaker condition in terms of Bregman divergence instead of standard L1 norm. However, we show in our proof that such a weaker bound suffices for the algorithm to still work. One technical contribution of our paper is to design distributions for all three domain setups. For the L2-L1 case, our distribution is slightly worse than optimal due to some extra complexity caused by domain asymmetry. In our paper, we also give two alternative distributions to the one here, which attain different Lipschitz constants. These yield improvements in different parameter regimes. For L1 geometries, since our local norm analysis only works with bounded estimators, we adopt an idea from previous work by Clarkson et al. Called clipping, where we appropriately truncate the difference estimator. We show the analysis still works under this modification. For the L2-L2 setup, We propose two sampling distributions which both achieve the choice of Lipschitz constant listed here. Next, Kevin will conclude the overview of our algorithm by discussing the implementation of our iterations in near constant time.
We now turn our attention to the efficient implementation of our L1-L1 variance-reduced algorithm. Recall that the iterates are recursively defined by the displayed subproblem, which is a minimization of a linear term regularized by two Bregman divergences. The relevant Bregman divergence here is KL divergence. One center is x0, a fixed anchor point computed at the beginning of the inner loop, and one is the previous iterator. The linear term is our variance-reduced stochastic gradient estimator. It's the sum of a gradient operator at x0, which is fixed throughout the inner loop, and a changing one-sparse component. The key difficulty is to implement these steps in amortized, near constant time by using the recursion structure, despite the fact that the linear terms may always be dense. It's not hard to see that in closed form, the recursion satisfies. Xt plus 1 is proportional to xt exponentiated by a scaling factor less than 1, multiplied entry-wise by x with v, where v is fixed. Finally, the jth coordinate is modified by the one-sparse component. We now boil the implementation down to a data structure maintenance problem. The goal is to maintain forms of query access to points recursively defined as in the previous slide. We can think of this as a nonlinear kinetic data structure problem. Kappa takes on the role of a damping coefficient. V is like a fixed velocity, and CTEJ is like a time-varying drift component. We now state the interface that we need out of our data structure, which we call approx x maintainer. It needs to support two kinds of updates in near constant time. The first, which we call dense step, exponentiates the current iterate by kappa and multiplies by a fixed dense vector, then renormalizes. The second, which we call multisparse, exponentiates a single coordinate and then renormalizes. Clearly, each iteration of our method is the composition of a dense step and a multisparse. It also needs to support two kinds of queries. The first asks for coordinates of the current iterate, and the second asks to sample from it. We need sampling access to compute our estimators. Here, we note that both operations are robust, up to inverse polynomial error entry-wise. In our paper, the interface also provides update and query access to running sums. We'll skip this for simplicity. For starters, we're going to solve this problem in the easier case, when the drift term is uniformly 0. In this case, we define a vector delta t, so that xt is proportional to x0 times x of delta t. The recursion on delta t is delta t plus 1 is kappa delta t plus a fixed vector. We can rewrite this recursion in a much easier way. For some fixed vector bar delta, it's not hard to see that xt is proportional to x0 times x of some multiple of bar delta, where the multiple only depends on kappa and t. We actually develop a more general data structure, which can maintain access to queries of the form x0 times x of sigma times delta bar. Sigma is allowed to be anywhere in the range sigma min to 1, where sigma min is inverse polynomial, not just values of the form 1 minus kappa t. The bottleneck for this is actually just estimating the normalizing constant of x sigma. Since x0 and bar delta is stored explicitly, we can compute any coordinate of x sigma in constant time. So we just need to normalize it onto the simplex. Once we can approximate normalizing constants, the sampling problem is pretty straightforward, since we can just maintain a tree of partial sums. So we won't discuss it here. Okay, so at this point, we just need to figure out how to estimate the normalizing constant of x sigma. For this, we develop a really simple data structure called scale maintainer, parameterized by x0, bar delta, and some approximation tolerance epsilon, which is inverse polynomially small. The goal is simple. We want to pay O tilde n initialization costs, so that for any query sigma in the relevant range, we can return a 1 plus minus epsilon approximation to the normalizing constant in near constant time. The first idea is to notice that if sigma delta has range bounded by O of log n, then a degree O of log n Taylor approximation is good enough. If we have this bounded range, then we can just pre-compute all the inner products of x0 and delta of the cube, and linearly combine them on a query. Luckily, everybody outside this range basically doesn't affect the normalization constant, since it's being exponentiated, so we can truncate them. The key thing to note here is that the relevant range depends on the query sigma. So, the second idea is to bucket the time scale by powers of 2, which define different truncation thresholds depending on how big sigma is. We can just pre-compute all these truncated inner products. Finally, for the final data structure, we need to make sure that we support deleting coordinates. To do this, in each of the time buckets, we also pre-compute bucketed ranges of active coordinates in ranges of log n. When all the coordinates in the top bucket get deleted, we shift the active bucket to the next range. At this point, we're basically done. Our final data structure uses the same tricks as in binomial heaps, keeping track of log many scale maintainer instances of different sizes, which all get updated every iteration. The rank k scale maintainer is associated with some subset of coordinates with size at most 2 to the k. So, to implement dense depth, we just increment all data structures. For both sparse, we delete a coordinate from its current data structure and make a new rank 0 data structure. Finally, we merge any data structure to the same rank, ensure this doesn't hurt or amortize complexity too much, and that's the entire implementation. Yujia will now describe our applications and conclude the talk.
We now discuss applications of our methods. First, we show how to modify our algorithms to give efficient solvers for a few computational geometry problems. For instance, the maximum mean square problem asks for a given polyhedron induced by m half spaces in n-dimensional space, the position of a point inside it that maximizes the smallest distance to any faces of the polyhedron. In previous work, it has been shown that one can reduce the problem to solving O1 L2 L1 games in the bilinear matrix games form. Applying our method on the objective thus directly gives a runtime of nnz plus rho times square root nnz times RCS times epsilon inverse, where rho is some geometry measure of the polyhedron. Prior work by Alan Zhu, Liao, and Yuan in 2014 gives a primal dual algorithm with complexity scaling as mn plus rho times m square root n times epsilon inverse. It is worth noting that their method requires first randomly rotating the data, so it loses sparsity structure and has a real dependence on dimension. Our method always offers improvements for sparse data and further improvements on the numerical sparsity. A problem of similar flavor is the minimum enclosing ball, which asks to find a ball with minimum radius that it includes all m points lying in the n-dimensional space. The reduction to NL to regularized bilinear saddle point problem has also been shown in previous work. We apply a slight variant of our saddle point algorithm on the strong monotonicity to incorporate the regularization term. We again obtain the runtime improvements for sparse and numerically sparse matrices compared to prior art. For the last application, we show how to apply our L2 minimax solver to solving standard linear regression problems, which can be written equivalently as bilinear games with L2 geometry. Here, when A transpose A is strongly convex with eigenvalues lower bounded by mu, we can also apply the strongly monotone variant of our method to find an approximate solution in time nnz plus square root nnz times this L parameter over square root mu. This result is particularly interesting in the case when A is entry-wise non-negative. In that case, we can show our L is actually upper bounded by square root m plus n times operator norm of A, which improves by a factor of square root nnz over m plus n over the result achieved by accelerated gradient descent for regression, which is the state-of-the-art for some parameter regimes, unconditionally on numerical sparsity. This is similar to wins achieved by our prior work for L1 geometries. In the regime where A is numerically sparse as we define here, our method in the unaccelerated case also improves by a factor of at least square root L over mu over previous work, including SVRG and a recent sampling-based method for exploiting the numerical sparsity for solving regression. In conclusion, the key takeaways of the talk are the following three main conceptual or technical contributions of the paper, which we believe are of independent interest. The first is our introduction of coordinate methods for minimax optimization, which push current stochastic first-order methods to an extreme. We couple our coordinate sparse gradient estimators with novel sampling distribution design and a tailored analysis based on local norms in order to achieve the tightest runtime bounds for a variety of large-scale matrix problems, capturing fine-grained notions such as sparsity and numerical sparsity. The second is the design of data structures for efficient mirror descent steps under structure-dense operations, which are particularly interesting in the case of nonlinear Bregman projection updates, as in simplex constraint problems. This efficient implementation is a key component to attaining our fastest runtime bounds and may spur further development of coordinate methods more generally. The third is the application of our new algorithms to obtain faster algorithms for solving various problems arising in computational geometry and linear regression. We hope our results offer new perspectives and tools for large-scale optimization algorithm design more broadly. Thank you so much for your interest in our work, and feel free to check out the full paper online.